In the last lecture, we discussed how the voltage and resistance standards are defined using the quantum transport phenomena, namely the Josephson effect and quantum Hall effect. Josephson effect, precisely the AC Josephson effect to define the voltage standard, and quantum Hall effect to define the resistance standard. In this lecture, we will look into how the current standards are defined using quantum transport phenomena. We will address quantum current standard and use of single electron pump to realize quantum source for current and quantized source for current, metallic and semiconducting single electron pumps, and eventually close with a short discussion on quantum electrical metrology triangle. Current is one of the fundamental electrical quantity, and the unit of current, ampere, is one of the 7 base units in metrology. But interestingly, a clear quantum mechanical definition, a precise definition using fundamental parameters, for current has been realized only very recently in 2019, one and a half year back. Historically, and until 2019, the current is defined. The unit of current, the ampere, is defined as follows. This is the old definition until 2019. The ampere is the constant current when maintained into straight parallel conductors of infinite length, really long wires with negligible cross section, which are placed 1 meter apart, will exert a force of 2 into 10 to the power 7, 10 to the power minus 7 Newton per meter of length. That is the definition for current. And if you compare how the standard for resistance and voltage are defined, that involves only fundamental constants, such as Planck's constant, charge of an electron, mostly, right? Now, if you look at the definition for ampere, which is the unit of current, which is interestingly one of the 7 base units in the metrology, in the SI system, it is defined in terms of, first of all, meter is there. Then there is a force that is defined or calibrated using some kind of balance, watt balance. So it is, if you compare with the voltage and the resistance standard, this standard is pretty much, I would say, ill-defined until 2019. Now let's look at what is the new definition and how that definition has been realized using the certain fundamental phenomena in quantum transport. So the definition for ampere, the unit of current, is basically charge per time, so charge of 1 coulomb, and time is 1 second. So 1 coulomb per second, that is ampere, right? So the coulomb is basically defined as this number here, because the charge of electron is this many coulomb. This is 1 coulomb, and this is 1 second. because 1 second is defined in terms of the hyperfine transition of ground state of the cesium-133 atom. That is basically this many periods of radiation. Okay. That is correspond to 1 second. So the ampere definition is given by this, where E divided by 1.602 into 10 to the power minus 19 is the Coulomb, and delta nu Cs divided by this number is the inverse of second. So this is basically an ampere. So if you look at what is 1 ampere, it is basically 6.24 into 10 to the power 18 electrons per second. That's what it is. You look at how many electrons need to go through per second. That's basically 6.24 into 10 to the power 18 electrons per second. That is 1 ampere. And charge is quantized, and charge is discrete. And the best, cleanest, and most straightforward way to define the current would be to define it in terms of the number of electrons it passed by per second. So that is the new hope, and that is how now the current would be defined, a unit of current would be defined. Okay. So the point here is this would be the number of electron per second. That means this is the frequency by which the electrons need to pass through a second per second in a circuit to say that we have 1 ampere of current is flowing through. So this is nothing but it's actually a frequency number. Okay. So the problem now boils down to generation and transfer of electrons periodically through a circuit with certain frequency. And current I is defined in terms of charge of electron and frequency. And the assumption here, which is pretty true, is frequency is something which we can define, achieve, and measure without much inaccuracy, or with a very high level of accuracy, we can define frequencies in metrology. Okay, we can generate and apply and measure in metrology. So the current is nothing but I is equal to E into F, where E is the charge of electron and F is the frequency. So, but now the problem is the generation and transfer of electrons one by one, because now it is defined in terms of the number of electrons per unit time. So we need to have a control over the generation of electron and transfer of electron through circuit to define the unit of current precisely. And that is what we are going to discuss. So we know that the easiest way, and probably the most fundamental way of generating electrons and transferring it through a circuit in a controlled way is using single electron devices, such as single electron transistors or quantum dots, using the phenomenon of Coulomb blockade and Coulomb blockade oscillations. So in the single electron charging regime in a quantum dot, a rough schematic is given here. We have two tunnel junctions and there is a quantum dot in the middle, which is coupled to source and drain, and this quantum dot is coupled to a gate and a voltage source, which is the gate voltage. And in the low voltage regime, when the applied voltage or the energy corresponding to applied voltage is less than the charging energy, usually the transport is blocked and you can get current through system by adjusting the gate voltage, and you will get a series of oscillations, and those are the Coulomb blockade oscillation. And the transport in this regime, whenever you are on a Coulomb blockade peak, is by single electron charging discharging phenomena. That means the number of electrons on the dot or the charge state n varies between n and n plus 1. N when the dot is empty, n plus 1 the electron jumps on the dot, then back to n when the electron jumps out of the dot. So this is basically saying that the single electron charging phenomena is basically giving you a periodic, I would not say periodic, but a regular source of electrons, or a periodic, electrons pass through the circuit one by one. Now that is why it's called single electron charging. But though it is going to give you a source for single electron, or circuit, or the electrons pass through the circuit one by one, but you don't have a completely perfect control of the number of electrons passing per second, because the tunneling events are random across these two barriers, and there is basically a statistics built into it. So to make the circuit more precise and a better source for single electron, generally what is used is a 3-junction circuit, or you can say there are 2 common dots in series. So adding one more common dot will make sure that the tunneling is more precise, periodic and correlated. The reason we know from the charging diagram for double quantum dot that it need to go through 3 electron configuration, different electron configuration in a cyclic manner. For example, if you start with N1 and N2, to get an electron going through this, we need to be at one of the triple point where these 3 charge states are actually degenerate, and the electron, the transfer of electron is in a cyclic manner. For example, N1 N2, then N1 plus 1 N2, the next moment, then next moment is second electron will jump out, okay, then eventually you will reach back to N1 N2, okay. So the presence of second dot makes sure that this electron tunnels here only after this electron tunnel out, okay, then only the next electron can come in, okay. So there are less chance of having effects such as co-tunneling, and better correlation between the tunneling events. What that means, you will get a better control on the rate of electrons which is going through the second. Okay. And the circuit, the transfer of electrons through circuit is also controlled by adjusting the gate voltage. So you can basically make sure that the electron which reaches here doesn't tunnel to the second dot just by changing this gate voltage, so that you can lock this electron here such that this doesn't tunnel back, this doesn't tunnel in, because you can vary this gate voltage away from the triple point so that the electron will be locked here. Then next moment you can basically bring the gate voltage so that this dot or the condition correspond to the triple point. Okay, then this electron can tunnel in. So the tunneling event of this electron from one dot to other dot you can actually control very precisely in this situation. Okay, so you can make the dot on or off the triple point, individual dot, and you can control the tunneling of electron, the sequential tunneling of electron in a periodic manner just by using gate voltage pulses. That is the technology of single electron pump. Usually you have many dots, but you can also achieve the single electron pumping phenomena with just 2 dots. But of course, better control can be achieved by adding more dots or more tunnel junctions in series. So the idea here is you have 2 dots, the electron can tunnel in, then for this electron to move to the next dot, you can bring that dot into tunneling position or favorable for tunneling, and next you can actually make this electron tunnel out to the source, and you can also make sure that this electron doesn't tunnel back to the first dot just by adjusting that gate voltage using voltage pulses. So that is the overall idea. So what you're doing is you are going around this triple point, but each of these charge configurations you control by gate voltage pulses. That's the idea. So you have N1 and N2, and you decide when you want this configuration, and you decide when you want this configuration, and back to this configuration. So this tunneling events you control by controlling the gate voltage pulses. That is the idea. That is the idea of single electron pumps. So these are turnstiles. They're also called single electron turnstiles. Now, let us look at one of the first realization of this single electron turnstile using metallic single electron pumps. So in this case, what we have is tunnel junctions made of metals. So you have 3 junctions in series, that means 2 dots, and you can control the electrostatic potential of these 2 dots by these voltages U1 and U2. They are coupled to these junctions using C1 and C2. Okay, and there is a source drain voltage across the whole circuit, and you will get a honeycomb shaped charge stability diagram for the system. Here you have one of the voltages U1, other voltages U2. Now the idea here is you can make these 2 junctions, these 2 dots favorable for the electron to occupy periodically by using gate voltage pulses. So that is the rate at which the electron will transfer through the circuit. And when you have 4 megahertz transfer rate, you can work out what would be the current. 4 megahertz correspond to a current I equal to E the electronic charge into F. F is 4 megahertz. That will give you approximately 0.64 picoampere, and that is what they are getting. So approximately when F is 4 megahertz, you have approximately 0.64 picoampere, and you can also change the phase of the pulse so that the electron travels backwards, backwards, the forward current or reverse current. Then you get minus 0.64 picoampere of current. This is published in this landmark paper. This is like, imagine that you have a series of gates, turnstile gates, which will allow only one person to pass through. Here only one electron to pass through, and this electron goes here first, then this gate closes, then this electron cannot tunnel back. Now once this is closed, electron is locked here, then this gate's open, then electron will go here, then after that, immediately after that, this gate will close. This electron reaches here, so electron cannot come back, and then this will open. This goes in sequence. So this opening and closing of these gates are controlled by the voltage pulses which is applied to the gates C1 and C2. So you can control the transfer through the whole device like like the movement through a turnstile gate, and that is why these are called single electron turnstiles. And in this plot, what we have is the current as a function of frequency, and you can see that the relation is a straight line because current is proportional to frequency and E is a constant, the charge of electron. So you can see that current is proportional to frequency, and whatever they got is pretty accurate. But how accurate and how stable it is, that we will see in the coming slides. So this is the fundamental idea of realizing current standard using single electron tunneling phenomena and single electron pumps or single electron turnstiles. So here, this is a slightly more advanced single electron pump. What we have here is a 7-junction pump. It's not a 3-junction pump, it's a 7-junction pump. Okay. And you also have at the end, you also have some kind of an island. Okay. That island can actually collect this electron when it tunnels through, and that charge on that island can be detected using a charge sensor. Okay, so you have electrons going through these tunnel junctions one by one, and this movement of electrons through these tunnel junctions are controlled by these gate voltages, just like what we discussed in the previous slide. But there are 7 junctions, not 3. Okay, and when you add more and more junctions, you will have no backward tunneling, no co-tunneling very much. Co-tunneling is a phenomenon where the electron can exchange position, 2 electrons can exchange position, but the charge state will not change very much. Okay, so the overall effect is you will have current flowing through, but the charge state is same, and this co-tunneling time scale is within the time uncertainty. So you don't really, this, even though it's not energetically favorable, but it can still happen. You can still have that phenomena happening. Okay, that is co-tunneling. This electron moves here. By the time another electron moves here, but these two things happen very, very fast within the time scale of quantum energy time uncertainty relation. Okay. Now, having many junctions, what you'll have is you have no backward tunneling and you have reduced co-tunneling, and that will improve or increase your accuracy to 15 parts in billion. Okay, and the idea here is you have many islands. This is just a cartoon. So first you make sure that electron is locked here by one of the gate voltages. Okay, then this is the representation of how the potential landscape changes corresponding to these islands when the electrons move through. Okay, so in this situation you have the electron in one of the island. Next moment you can change the pulse so that this island is not favorable for the electron to occupy, but this is suddenly favorable because of the gate voltage is changed in that manner. So electron will move here, next moment will be here, next moment here, next moment here. But this multi-junction circuit, you have 1, 2, 3, 4, 5 junctions in this diagram. Here we have 7 junctions. Okay. So this multi-junction circuit, it makes sure that this electron cannot come back, because there is no way that electron can come back through all these series of junctions. If there's only one junction, the co-tunneling even can actually bring the electron back. You can have electron tunnel back because of co-tunneling phenomena. But here you have many junctions and co-tunneling is not really favorable. So this will have better control and better accuracy in defining this current standard. Now, the issue with these metallic tunnel junctions are, first of all, these tunnel junctions are fixed tunnel barrier, so you cannot control the tunnel barrier. These tunnel barriers have this transparency or whatever it is defined when it is fabricated. You cannot change it later. It is basically the thickness of the tunnel barrier plus whatever the resistance, normal state resistance of the tunnel barrier. Okay? Normal state resistance of the junction, thickness of the junction, and the normal state resistance of the junction. These two factors will define the barrier, tunnel barrier, and you cannot change it. So that means the capacitance of tunnel barrier you cannot change, the resistance of tunnel barrier you cannot change. Okay, there is not much controllability. So if you look at these many junction circuits, all these events need to happen by single electron charging phenomena. And if you consider the whole circuit, the overall time scale by which you can operate the circuit is very long, or overall frequency scale always is much lower, only in megahertz range. What that means is, if you look at megahertz tunnel rate, the current that correspond to is picoampere or sub-picoampere. That means you cannot define a current standard with really high current output, like in nanoamperes, microamperes, or milliampere range with this tunnel junction. You cannot do that because these junctions, these devices can operate only in lower frequency range, megahertz range. If you add more and more junctions, the frequency will go down further. Though you will increase, you will get a better accuracy, you will improve the accuracy, but at the expense of the current. When you have more current, you need fewer junctions, fewer number of junctions, but then your accuracy will be compromised. So that is the issue here. So the solution is, you need something where you can modulate the tunnel barrier, or you can modify the tunnel barrier by voltages periodically. And that is not possible with these metallic tunnel junction cell systems or metallic single electron pumps. Okay, and for that we need to look into some other material system where all these parameters are actually controllable. Now, compared to the metallic single electron pumps, the semiconductor single electron pumps based on semiconductor quantum dots, especially precisely the gated semiconductor quantum dots, can operate in much faster time scale or at much higher frequency. These gated quantum dots we can operate by modulating these gates in gigahertz time scales. We can apply voltage pulses on this gate and modulate the tunnel barrier, modulate the shape. You can modulate pretty much every parameter of the dot by the voltage pulses, unlike the metallic tunnel junction systems. So in this recent experiment, what they have done is they have single quantum dot, and you will see that this is a much simpler design and easy to operate compared to metallic system. The metallic system could be easy to fabricate, but the semiconducting systems have a lot more advantages. Okay, so here what you have is, you have a single quantum dot defined by two gates, and this is an illustration of the potential landscape as a function of the gate voltage pulses. So you have pulses applied to one of the gates, in this case the gate on the left. So to start with, you have this tunnel barrier nearly almost zero, and this tunnel barrier you are not changing. This tunnel barrier is kept at a specific height, and the tunneling through that tunnel barrier is defined by that tunnel barrier height, and it is you can think that there is a reasonable tunnel rate through that tunnel barrier. Okay, and this illustrates the cycle. So what you have is you start with one tunnel barrier, other tunnel barrier is very low, kept it kept below the Fermi level, so that you can fill the electron up to this point. Then what you do is you apply a pulse so that this tunnel barrier is raised, and you make sure that you're always a single electron charging regime. What that means is suddenly you will end up with one electron in the dot, and all the other electrons will flow out. Okay, so you have the electrons filled up to one point, then you raise the tunnel barrier, so one electron will get trapped, and you raise this tunnel barrier further by applying the pulse, so this electron will escape through the other side. Because this side there is no escape, because you make sure that these tunnel barriers are really high, so there is no path for the electron to escape the left side, to the left side. So it's basically you fill electron, rise it, then hold it, then rise it further, so the electron will go. So this pulse sequence, by this pulse sequence, you can get a more or less periodic flow of electron through circuit, but in this case, the time scale is really fast, and I would say the limiting time scale would be here this tunnel barrier height, or the tunnel rate through this tunnel barrier, because this gate pulse you can operate really fast time scale, but the tunnel rate through this barrier would be the limiting case to define this to realize this single electron pumping sequence. And the accuracy what they have claimed is 1 parts per million, and this is basically the accuracy for various VG2 gate voltages. Okay, whatever is here. And a similar geometry and similar concept, you have a silicon single electron pumping device. This is realized on a gallium arsenide heterostructure wafer. This on a silicon with a MOSFET geometry. You have something like a nanowire, silicon nanowire, and you have two gates, and you have actually two islands. In this case, you have only one island, or one basically quantum dot. In this case, you have two quantum dots, and this is a picture of the actual device, and this is the schematic, of the circuit diagram. So you have two quantum dots, and one of the quantum dot is your pump, and the other quantum dot is a sensor. It's a collecting region. Okay, so you make this electron tunnel in a similar fashion as described here. The cycle is here. We'll come to the cycle in a minute. And what you do here is you tune the dots in such a way that this dot can accept electrons over time, one by one. The electrons will get collected there, and it is capacitively coupled to a electrometer, which senses how many electrons have been collected, and you measure this potential as a function of time. Basically, you are measuring the current through this device, which will tell you what is the potential of this island, which is proportional to the number of electrons collected on the island, basically proportional to charging events. So you can see as a function of time, what you are seeing is the potential is rising, or the current through the potential is rising, or the current through this device is actually changing. Okay, when you start, so you have when you have more and more electrons collected on it, you have more negative charge built upon, and what you are seeing is you have a reduction in the current in a step-like fashion. So what this experiment is telling you is that you can have electrons tunneling through this in a very periodic manner, and the discrete changes in the island potential is detected by a discrete change in the current through this sensor. This is an electrometer. Okay, so now let's go back to the sequence here. So what you have here is, again, you start with this situation where you have nothing in the no electrons in these two dots, but you can see that this dot is slightly tuned to a lower energy so that you can collect more electrons. So you start by not having this tunnel barrier. Electrons fills into the dot. Suddenly you rise it, so one electron ends up. then you basically lower that, the electrons will get collected here, but this is a lower energy, so the electron doesn't go back. Okay. Now, but even if it goes back, you definitely you have this tunnel barrier which will stop it going all the way back. Then after that you rise it back, so you are in this initial state, but with one extra electron in the second island. And that electron will be detected by the current through this sensor here. And this is the one transfer cycle, and this is the pulse sequence. So when you do that over and over, every transfer cycle will get put one electron regularly into the island here, or into the island here, and that is what is detected by the change in a periodic discrete change in the current through the sensor. And you can find more details on this work in this paper. Okay, so now what we have discussed so far is the realization of single electron pumps and the realization of current standards using single electron tunneling phenomena, which is one of the fundamental quantum transport phenomena. And using the metallic single electron pumps, you can get up to like a picoampere, and here you can go to nanoampere range, or femtoampere to hundreds of picoampere to nanoampere range using semiconducting single electron pumps. Okay. Now we have discussed during the last lecture and this lecture how the fundamental electrical standards for voltage, resistance and current are defined using quantum transport phenomena. And the voltage standard is given by the voltage produced by a Josephson voltage standard, or it's a Josephson junction or an array of junctions. It is given by n is an integer, fj is a frequency, and kj is the Josephson constant, which is given here. Similarly, the resistance is given by Rk by I, where I is an integer. This by quantum Hall resistance or quantum Hall phenomena, where Rk is this constant h by E square, which is called von Klitzing constant. Similarly, the current standards are defined by Qs into Fz, where Fz is a frequency component, a frequency, and it's a current generated by single electron tunneling phenomena driving charge quanta of value Qs, where Qs is basically the charge of an electron. So what you are seeing here is all these three electrical standards, the voltage, resistance and current. These are all, the standards for all these are defined in terms of the fundamental constants E, H, E and H in various combinations, E by H or H by E square, like that. Okay. And these phenomena and this accuracy of the standards are verified independently. Of course, the current standard is something which has came up recently, and the accuracy of the current standard is not as high or as good as the voltage or the resistance standard, but of course this is a developing field. Okay, this is fastly developing field. Now, if you combine these three in one circuit, okay, that means you have voltage, you have resistance and you have current, then you can get some version of the Ohm's law. Okay, but here everything is defined by quantum transport phenomena, so we simply call, or we refer to that as quantum Ohm's law. Okay, so in this case, the voltage developed by Josephson junction, the resistance of a quantum Hall standard, and current due to a single electron standard. These three, if you combine these three using these relations, what you would see is Kj, Rk, Qs. Kj is the Josephson constant, Rk is the quantum Hall resistance constant or von Klitzing constant, and Qs is an electronic charge. If you combine all these three, this will give you 2, an exact numerical value. But now, one need to verify that in a single experiment, by combining these three, whether we get an exact value of 2 for the product of these three constants. That is the ultimate test for accuracy of these three standards. The reason here is the voltage, to test a voltage, you need resistance and current standards. To test a current, you need voltage and resistance standard, because these three are tied up together in an electrical circuit. So the accuracy of current, voltage, and resistance in a circuit need to be verified together. And constructing something called a triangular is a conceptual triangular circuit where one of the arm connects frequency to current, another arm connects frequencies to voltage. That is, this is the Josephson effect. This is a single electron tunneling phenomena. And another arm connects the voltage and current. That is a corner Hall phenomenon, corner Hall effect. Okay. So these three, combining these three phenomena in one experiment and verifying the accuracy of this product of these three constants, the Kj, Rk, and Qs, to 2 is the ultimate test for these standards. And that experiment is called quantum electrical metrology triangle experiment. And that is done under the assumption that there are errors in all the three constants. Okay, Qs is electrical charge that is supposed to be, that is the constant, but the assumption here is it has some extra error, epsilon e. Similarly, for Rk there is an error epsilon k, and Kj there is an error epsilon j. So to the first order, when you combine all the three, you are supposed to get 2 plus some small error. And how small or how big that error, one need to determine, and that is the aim of this ultimate metrology experiment, which is called quantum electrical metrology triangle experiment. So the experiment basically checks how much the value of this product depart from 2. Okay. Now, there are various versions of these experiments are in progress. So in this lecture, we will discuss one experiment, which discuss how to close this quantum metrology triangle, the QMT, directly. So here is a schematic of the diagram of the concept or the circuit. It's not a concept, this experiment is performed. Okay. What you have is, you have a single electron SET pump based current arm, you have a resistance arm, and you have a voltage arm. These three are linked. So the single electron pump and the voltage, they are powered by phase locked frequency generator. Okay. Of course, these two are not operating at the same frequency, but they are phase locked. Okay. Now, the current generated by the single electron tunneling pumps are low. So what you do to get an appreciable voltage across a standardized resistance? Of course, theoretically you want a quantum Hall resistor, but this resistor is calibrated using quantum Hall effect to really high precision. And of course, this is a voltage, Josephson voltage standard, which generates the voltage. So idea here is, you have the single electron tunneling phenomena and the current generated that gets amplified by something called a cryogenic current comparator. That is basically a current amplifier with a very, very high precision, with the metrology standard precision, with a very high gain of 20,000 or so. The details of this current comparator will not go over much, but this is a current preamplifier. Okay, so you have phase locked Josephson voltage standard and SET pump, and this SET pump current is amplified and ran across a quantum Hall resistor. That's what's happening here. So you have a current which is run through this resistor, and that will develop a voltage drop, and that voltage drop will be compared with the Josephson voltage produced by this JVS voltage standard using something called null detector. This basically tells how much of these two voltages are off. Okay, so it basically matches the voltage coming from voltage drop across this resistor and the voltage produced by the Josephson they should be exact in principle when you realize this. So what you will see is these two voltages should be exact, so that this null detector says there is no difference, and that is what you are looking for. Any variation from this exactness or any change, any reading from the null detector is the error in the whole experiment. So you have V is equal to I into R kind of relation, and by substituting the constants from the previous slide, what you can get, you can test something called a charge. Okay, you can substitute this and rearrange, and what you will get is you will have something like Qx. That Qx you have not told what that is. Okay, assume that that's supposed to be Qs, the charge of electron, but how much that Qx or the charge that you measure differs or varies or departs from the charge of electron, that is the error. Because now you have combined all the three, and all the error you have absorbed in the charge of electron. Okay, so now Qx is given by this formula here, and what you do is you compare that Qx to the E-codata value. E-codata is basically the best available value for this fundamental constant, the charge of electron. The codata is Committee on Data for Science and Technology, that is the codata, and that E is basically this number here. You compare this Qx to this number and determine how much error is there. That error is basically tells you how good the closure of this quantum metrology triangle is, or how close they are, with how close or what is the success of this experiment. Okay, so how much error is there? So you can actually determine what is the current as a function of frequency, and this is how the current is varying as a function of frequency. So the middle flat portion is basically telling you the stable current regime at lower bias. Okay, and this current is of course will get amplified by this current comparator, and then that is getting dropped across this resistor. Okay, but this is the current generated as a function of frequency, and you can see the current is pretty stable, and this is the magnified view for the 30 megahertz and 10 megahertz, these two curves here. So you can see that the 10 megahertz current is I equal to E into F, that is 1.602 picoampere, and that is what is approximately. And this is theoretical value, and this should be 30 megahertz should be 3 times of this. That should be 4.80, and that's what you are measuring here. But there is of course a considerable amount of error in the measurement of the current through the system. So overall accuracy of the whole experiment will depend upon the exercise will depend upon the error here also. Okay, so now what we have here is approximately 40 femtoampere of error in the current measurement. Okay, that's what you have in this experiment. Now by comparing the charge of electron that you calculate from this experiment and come with the E-codata value, you can calculate what is the error that is in E. The error in E is something like of the order of delta E by E is of the order of few 1 to between basically few 10 to the power minus 4. That's what this value is here. Okay, so this is when you pump the single electron circuit with the 37.16 megahertz, and with the Josephson junction NJ is 8. Okay, so and this is how this is calculated using this is error bar here is generated by taking various this is the error bar here, and this is how much it varies over various number of measurements. Okay, that's what it is. So this is an interesting experiment. I would say this very important experiment, interesting experiment in quantum metrology, quantum electrical metrology, where they have checked the accuracy of these three fundamental phenomena together. So because you need to have you need to have an accurate voltage measure, accurate current measure, and accurate resistance measure. And when you combine all the three, Of course, you also need to make sure that these, the product of these three should be 2. That is the check that you're going to do. That is you are doing in this experiment. Okay, and but eventually in this experiment, what they have done is instead of checking that, you check how the charge E that varies from the E coordinate value, and you can see that that is pretty good because it is 10 to the power minus fourth of electronic charge, which is already which is a very small number, 10 to the power minus 19 coulomb. So it is, I would say the accuracy is basically 10 to the power minus 23 or something like coulomb. That is what we have in the electronic charge. Okay. So what we have done in this lecture and the previous lecture or in this module so far is we overview the use of quantum transport phenomena in defining fundamental electrical standards, namely the quantum Hall effect, the Josephson effect, the AC Josephson effect, and the single electron tunneling effect, and how these are, these fundamental basic physics concepts are used in high-end technology called quantum electrical metrology and quantum sensing.